Okay, let us go forward with another part, and this part it's really a topical part. It is a momentous time now because we go back to integrals. So the title here is, if I'm able to turn my pen on, okay, I'm able to do that. The title is Back to Integrals. So now we have Lagrange Theorem, the corollary of the Lagrange Theorem that says that if a function has derivative vanishing on an interval, then this function is constant on that interval. So we can go back to integral and compute them. And so first definition, the first remark, which is very important, is the following. Is the final formulation of the fundamental theorem of integral calculus. Remember that the theorem was the following. Let f from AB to R be continuous. It is very important that it is continuous. Capital F from AB to R associates to every x the integral between a and x of f. Then I recall you the three formulation. You have that for every x bar in AB, let me say that AB is open. It is not strictly necessary, but however, f of x, capital F of x minus capital F of x bar is equal to small f of x bar times x minus x bar plus little o of x minus x bar as x goes to x bar. This is the first. Second, which is completely equivalent, the limit for x going to x bar of f of x minus capital F of x bar divided by x minus x bar is equal to f of x bar. And third, now I just ask you to observe the following fact. First, this is the definition of derivative. This is also the definition of derivative, another definition totally equivalent that says that the derivative is the limit of the incremental ratio. Okay? So the third formulation, which is the final one, is the following: is f is differentiable at x bar, and capital F prime of x bar is little f of x bar. Okay? And this is the final formulation, and I will stress, I will highlight this. So when you read the fundamental theorem of integral calculus in book, you only find the third, and it is completely correct. In general, books that treat derivatives before the integral, which are the majority, can use the derivative already in the fundamental theorem of integral calculus. We did not have derivative when I explained you this theorem, so I had to use these other definitions, but it is totally equivalent. Nothing is lost here. Okay? But from now on, when people, including me, asks you the statement of the fundamental theorem of integral calculus, you can use this second statement. Okay? So, and now, just looking at this statement here, you can easily see that computing an integral reduces to the following problem. You want to integrate f. In order to do that, you have to understand of which functions small f is the derivative. This is in a vague terms. So let us make these terms more precise, and just 20 seconds. Okay, sorry. When you are at home, there are. So, and so the first definition, in order to go back to integral, is the following. It is definition of primitive of a function, of a continuous function. Of course, you can use the idea of primitives for functions that are not continuous, but I will not touch this point. When you look at books and you find the idea of generalized primitive, just close the book. It is not interesting. So, if you have f from AB to R continuous, a function capital F from AB to R continuous to in the whole interval AB, differentiable in AB open, and such that for every x in the open interval AB, you have f prime of x, capital F prime of x is equal to small f of x, is called a primitive of f. Okay? So in this sense, the primitive is the inverse of derivative, but there is an important difference. The derivative is unique and primitive is not. And another preliminary remark, if f, capital F, is a primitive of small f, then the function capital F plus C, where C is an arbitrary real number, an arbitrary real constant, is said, is a primitive of small f 2. So, if a function has a primitive, then it has infinitely many primitives. Just obtain varying C. Now the question can be whether there are other primitives. So the set of all primitives, how is it made? So first of all, another definition can be made. Since primitives are not unique, we give this definition. Given small f, again from AB to R, continuous in AB. The set of all primitives of small f is called the indefinite integral of f, and this denoted by this symbol here. It is like the symbol of integral that we already introduced, but it has no intervals here. And so again, first remark, the indefinite integral is not a function, it's a set of functions, okay? Remember that. Of course, it is not a number. The indefinite integral is not a function, but it is a set of functions. This is the first point. Second, as I said, the indefinite integral is infinite in the sense that the indefinite integral of a continuous function has be more elegant, contains infinitely many functions. Why? Indeed, given f from A, B to R continuous, we already know by the fundamental theorem of integral calculus, we already know that capital F, the integral function, integral between a and x of f of t dt, is a primitive of small f, since capital F prime is equal to small f. Moreover, by the previous observation, f plus c, so this function here is again a primitive of small f2 for every c in R. So we have infinitely many. Now, the theorem that says that the contrary is true. So, the theorem, which is the structure of the indefinite integral, that says the following. you have a function small f from AB to R, continuous in AB, and F1, F2 from AB to R are two primitives of F, then it means that there exists a real number C such that F1 of X is equal to F2 of X plus this number C for every X in AB. So the structure of the indefinite integral is very simple. This means that here you have a function f. I don't want to draw the function f because then, or for instance, yes, I can draw function f2, something like a parabola, why not? This is f. Then you know a primitive, for instance, this black function here. Capital F, 1. Now, every other primitive of small f is looks exactly like f1, except that it is vertically translated, like the Brown function here. It is just oh, what happens? Okay, vertically translated like that. Okay, it is not exactly vertically translated. Okay? So, the set of primitive, so the indefinite integral of f, small f, can be represented easily by translating vertically, in the vertical direction, the graph of a given primitive. And so the proof is elementary, it is really elementary. First, from the algebra of the derivatives, you have that f1 minus f2 is differentiable in AB, open. Then the derivative of f1 minus f2, f1 prime minus f2 prime is equal to f minus f, and this is 0. Okay? They share the same derivative, which is f. Now, since the domain of f1 minus f2 is an interval, then the Lagrange theorem states more exactly the corollary of the Lagrange theorem that we studied in the next lecture. So the corollary establishes that f1 minus f2 is a constant. So there is some C in R such that f1 is equal to f2 plus c. Then the theorem is proven. Okay? So, as a notation, so given a function f, so given a primitive, capital F, of some function small f, the usual graphical representation, the usual writing for the indefinite integral is the following. Indefinite integral of small f is equal to capital F plus c. But remember that here the indefinite integral is not a function, okay? This representation can be somewhat misleading in the sense that here this seems to be a function, but this is not. This is a set of function because it is not written, but one has to remember that C varies in all R. Okay? And then now we go to the result, which is the fundamental formula of integral calculus, which is not to be confused with the fundamental theorem of integral calculus. So here we have a theorem, much less important than the previous one, but less important from the fundamental point of view, from the point of view of establishing the theory, but more important from the point of view of computing, concrete computation of the integrals. So this is fundamental formula of integral calculus. That says the following fact. You have a function f from AB to R, which is continuous on the whole closed interval AB. Then, and you have, capital G is a primitive, an arbitrary primitive of small f, then the integral between a and b of f, so what we wanted to compute since some weeks, is equal to the difference of the values of the primitive in the extremes of integration, the extremes of the interval, g of b minus g of a. Proof. First, let us consider a particular primitive, which is the integral function f of x is equal to the integral between a and x of f of t in dt. Then, the integral between a and b of f of x in dx is equal to f of b. By definition, but this can be written as f of b minus 0, and now I will write 0 in a strange way, f of b minus the integral between a and a of f of x in dx. Why this is 0? It is 0 because this is the area between a and a, which is 0, or perhaps you can try to do that by the usual sums. Okay? And this is f of b minus f of a. So the formula here, the thesis, holds at least for one primitive, capital F. But since g is equal to f up to a constant, then it holds also for g. So now let g be a primitive of capital F, of small f. then by the previous proposition, there exists C in R such that F is equal to G plus C. Then, so as a consequence, the integral between A and B of f of x dx equal to f of b minus f of b a. This is equal, since f is equal to g plus c, to g of b plus c minus g of a minus c, and the two c's cancel each other, and one ends up with g of b minus g of a. And this is the end of the proof. Okay? So, I conclude with the following remark that goes towards physics 1. You will see that in mechanical systems, conservative mechanical systems, the potential energy, or in general the potential of a field, like the electrostatic or the gravitational field, is defined up to an arbitrary additive constant. As you will see, in particular for one-dimensional systems, or in case of central forces, one can define the potential with a little abuse of language as, for instance, in case of central forces, V of R is the distance between the point you are considering, where you are computing the potential, and the center of the force, for instance, the sun for gravitational force into the solar system. This is minus F of R dr. There is a minus here. And so V prime of R is equal to minus F of R. So in general, the arbitrary constant is fixed in such a way that the limit for R going to plus infinity of V of R is equal to 0. There is no potential at infinity. Okay, and now we have really all the tools in order to really compute the integral, and this will be the subject of next.